1995 is really a great year to be a developer on the NextStep platform. Why? What's so good about NextStep in 1995? Well, there's two things. Let's look at the kind of bigger, the longer term picture. Something that really excites me right now about the state of computing in 1995 is that we're on the cusp of the portable revolution. So this is what I did the presenter notes for my talk on. This is the latest in Pocket PCs, released 1995, and this nice big screen, touch screen. If you see a stylus, it's awesome. Batteries, like 2 AA batteries, it lasts for about a month. And this is a full PC, right? This is like a 1985 era PC architecture in a pocket-sized case that lasts for ages on a couple of batteries. So 1985, one of these, but in a big metal box. In a big metal box in 1987, you could get the Motorola 68030 CPU. What's important about the Motorola 68030? You can run NextStep on it. So we're maybe maybe a few years away. By 2000, we should be able to run Objective-C NextStep apps on a pocket device with a touch screen, maybe a color touch screen by then. Month of battery life on a couple of AA batteries. Can you imagine how brilliant it would be to carry your Objective-C NextStep system around in your pocket? And we'll be able to do this by the year 2000. This is really cool. But 1995 is the year that NextStep through the OpenStep platform will finally become mainstream. Because really, what are the options? I mean, you've got Microsoft and OS2, Microsoft and Windows NT, Microsoft and Windows 93, which they haven't even shipped yet. Like, Microsoft is basically destroying itself by competing with itself on so many different fronts, taking IBM with them. What's the other big desktop kind of enterprise software workstation vendors? There's some, but didn't I say OpenStep? Who worked on OpenStep? Next, and Sun. So everything's coming up OpenStep. This is the best year to be an Objective-C developer. Of course, if everything was awesome, then I wouldn't have much of a conference talk. I could just tell you how great life is going to be, and how by 1998 we will become the most valuable programmers in the industry. But we have to accept that not everything is going well. We have to accept that we are in a state of crisis in our industry. The object-oriented programming crisis? I'm not sure. I'll come back to that. So, of course, we're, hands up in here who programs or has programmed in Objective-C. I expected it to be kind of everyone because, this is the year of Objective-C. So we'll all have read the 1986 Object-Oriented Programming, an Evolutionary Approach by Brad Cox. Talks about ideas, I don't know whether, whether this has come up at all for you in the last couple of days, a guy called Douglas McElroy, who invented the Unix pipe. So he said in 1968 that the way that the software industry would mature would be to create factories of reusable components that can be composed together to make big applications. And then all of your kind of clever algorithmic programming can go into building these components. It would be like constructing an electronic device, such as the latest in Pocket PC technology, from a collection of components. People build transistors, ICs, resistors, capacitors. Someone else works out what they want their circuit to do and selects components from data sheets in order to make the thing that solves their problem. So then in the 1980s, Brad Cox said, well, let's create the software IC, the software integrated circuit. Turns out we can already do that, and it's the object. So let's build a system that lets us take low-level statements in a kind of standard programming language like C, compose them into methods on objects, use dynamism to select which of these software ICs we're going to use, bind them together in our runtime of our application. We've got ourselves an app. We've got ourselves a software system. He went further. 1992, so only a few years ago, he said, in response to Fred Brooks, what if there is a silver bullet in software engineering? And what if your competitors get there first? Of course, our competitors didn't get there first because we're on the object-oriented platform. We are doing the object-oriented software with the software ICs that was supposed to remove all of the incidental complexity from software engineering and just leave us with the admittedly still hard problem of doing whatever it is that our users need us to do. So, did that work? Is object-oriented programming the silver bullet? Are we in a situation where everybody is now an order of magnitude more productive because object-oriented programming has saved us? It's kind of hard to tell because it's very difficult to find an object-oriented programming. Even in 1995, even in the golden age of object-oriented programming, it's very difficult to find an object-oriented program. I thought last year I had really high hopes. So, 1994, a bunch of programmers from Sun who collaborated with Next on the OpenStep specification, hired a bunch of programmers from Next, bought, like a Smalltalk company or a few. I even heard from my colleagues at Lighthouse Design that they'd been talking to them about various projects. The famous OpenStep Apps company built the kind of keynote pages type word processor and presentation package, if anyone has used those things. They're working on a new object-oriented platform. This sounds great. This sounds like exactly what we want. And they're taking away the C stuff that makes Objective-C a little bit kind of gnarly and complex, which is really nice, because then we'll have a garbage-collected memory management system, so actually having object-oriented memory storage, which, even after 10 years of Objective-C, we're still waiting for from Next. We would have, presumably, more objectness. When I heard about it, this project was called Oak. They've since renamed it to apparently name it after a cup of coffee, presumably because their developers have to spend loads of time, late nights, drinking lots of coffee, debugging problems with the system. Because we're not in the object-oriented programming crisis at all. We're still in the imperative crisis. So 15 years ago, 20 years ago, Dijkstra and others said, hey, this imperative programming thing, it turns out it's really hard. And we've got to keep track of all these variables and all these changes that we're making and how things are temporally related to each other as we start at the beginning of this code and fall through to the end of the code. And then all of the people who were interested in object-oriented programming and working at Xerox PARC said, here's the thing. Here is a thing that stops you having to do imperative programming. Here is the thing that lets you decompose your system into a network of messages being sent between objects. Remember, it's the the interstices, that are the important bits, not the objects themselves. So this will make it a lot easier to think about what your software is doing, because each bit of software is actually tiny. It just does a couple of things, sends messages to other objects, and the behavior, the complex problem that we're actually trying to solve, the solution to that will be emergent from this from this network of objects. And what Objective-C gave us was a trapdoor. So we could go, turns out I haven't actually thought about object-oriented programming before, but I've done a lot of C. I'll open the trapdoor, and I'll write some C. I'll just shove it into this object, but I'll hide it. No one will know. It's just a little bit of C. And then the next time I need to write a method, I go, well, actually, like writing the C over there, that went all right. I'll write some more C over here. And then it turns out that my program is just a C program where my function calls are slow because they have to go through obj message send. Java has the trapdoor, except for direct pointer access. Other than that, it lets you write your imperative C programs with your semicolons and your brackets and all of the stuff that we've come to love from C. And it just lets us write one line that follows another in a sequential program. It lets us write static methods, so we don't even have to worry about creating objects and things like that. And it turns out that a Java program is just a C program. So, of course, object-oriented programming hasn't solved any problems. No one's tried to use it. So I thought I'd take one for the team. I thought I'd try, and I realize that this is novel, that this has not been attempted before. Even in 1995, no one has got to this position yet. I thought I would try to write an app using object-oriented programming. And I thought I'd see how it works. So this is the game of life, and it has simple. Well, you all know about next step menus, so I don't need to explain what's going on there. But the game of life has fairly easy but complex rules. Or rather complicated. It's not complex, but it is complicated. But it turns out that you can write an app to do it in a few hours, which is sufficient for doing a demo at all. Now, I want to take the rules of object-oriented programming, the rules of Objective-C, and try to drive this game of life app to the point where it's an object-oriented application. Now, I admit, I didn't get this right first time, and I had to kind of go through and think about, I've got some imperative stuff going on here. I need to push this into object-oriented programming. I need to actually drive myself to do this as a collection of messages and not as a linear flow of statements. But I eventually got there. So my rules. Always be messaging. Everything in this application should be messages sent between objects. There shouldn't be temporal cohesion. So if things need to happen in a particular order, it's because the object that is going to receive a message has to be resolved before you can send it a message. This is like the fundamental thing in object-oriented programming that gives us sequencing, is that you have to resolve the receiver of an object and the selector that you're sending it before you can send that message. So if we build everything out of objects and messages, then even the sequence of code as the messages propagate through this network will be an emergent property of the system. So we don't have to think about it. We don't have to think, should I do this before that? Always be returning, by which I mean always be returning objects, and we'll see what that means there shortly. And build messages out of messages. So let's start with always be messaging. Now, we saw the game of life is a grid, and each grid is was either shaded white or black. Each cell on the grid was either shaded white or black, corresponding to whether the cell is living or dead. And the rules are that as the simulation ticks, as time advances in the simulation, each cell looks at its neighbors, and based on whether this cell is alive or dead, and the number of cells around it that are alive or dead, it will become either alive or dead in the next iteration. That's a lot of ifs. That's a lot of conditions. So, of course, we expect, as C programmers, to see a lot of complexity in the code that encapsulates all of these conditions, and no, I lied, it's just a message sent to an object, right? How can that work? Where have my if statements gone? How does the cell know whether it's alive or dead? Well, I answered that question back when I created the cell. Not at the time that I need to know the answer to the question, but at the time that I could answer the question. So my live cell knows what states it can go into next. And it turns out that there's a value for if it has 0 living neighbors, a value for if it has 1 living neighbor, a value for if it has 2, 3, and so on up to 8. Which sounds like a switch statement, unless you realize that having outcomes of going from a number to a result is an array lookup. And so you just send a message to an array and ask, what object do I get back? And that's your answer. So the neighbors themselves also know whether they are alive or dead because they worked it out back when they were created. So all of those if statements that had to go into my weird English language discussion of how the rules work have disappeared. McCabe complexity metric, cyclomatic complexity, is a thing that people basically go like, this is how hard this code is. It's 1 plus the number of conditions and loop returns you have in your code. It's 1. So, in fact, for the entire app, there are no conditional statements, no switch statements, no for loops, no while loops, no C. Well, there's a little bit of C because it's Objective-C and we have to do some stuff. But cyclomatic complexity, McCabe complexity, whatever you want to call it, throughout the entire app is 1. Because it turns out if we do object-oriented programming, we don't have to go through I've done these things, now what should I do next? Because polymorphism can answer that question for us. We can choose what object is the recipient of a message. I said no for loops, no while loops. How do we go through every square on this grid if I'm not going to loop over the squares in the grid? Well, just ask the grid to do it for us. So we have this visitation is kind of like keeping track. It's like a cursor. It's like an iterator in something like C++, in an imperative programming language. And then we say, right, we know how many of these things there are, so that many times, could you please go through and send a message to whatever is the next cell in this grid, collecting the results. So we might go through this one first, and then go through row-wise, then column-wise. It might go in a different order. It might do all of them in parallel and collect the results. I'm not telling you which way it does it. The code is not telling me which way it does it. The code is telling me which messages go to which objects. And then the whole system chooses how it solves this problem. Now, let's say that I were not me. Let's say that I were Marcel. I would probably, instead of that number with integer times thing, do something like this. That is why Marcel is a programmer and I'm a manager. Because this is the kind of higher order messaging. You can think of this as, I want to do this thing a bunch of times. So I want to modify how this message is used. So I'll create an object that captures how I want to do the modification. And then I'll send it the thing that I want to do, and it will modify it, and it will pass it through. So it's like kind of a composition in a different programming paradigm. Or you could think of it as there is a function that does visit next n squared times, and I'm doing the n squared times bit, the first parameter, and saving that off as a function that will then return another function to which I apply the next part, maybe. So we don't want a sequence at all, which is where we kind of bump into AppKit, the new UI framework from OpenStep. I don't know whether any of you have managed to port your code to AppKit yet. Because drawing is a sequence of procedures that are applied to a global hidden state variable. So, this is the most C you could get in your non-object-oriented program. Or we could just reuse that visitor pattern that we had for asking the cell what state it should go into, and just ask it to give us the drawing commands that we want, and apply those drawing commands to the context. Again, I haven't told you in which order these cells get drawn onto the grid, but we do know we end up with a completely drawn grid. We still don't have any branches or loops or conditions. We're just sending messages to objects. Because Next went a little bit weird with object-oriented programming in the OpenStep release, this method returns void, which I kind of found is not how to do an object-oriented program, because it forces you to sequence things. You can't say, right, this method is going to do its thing and then return an object to which I can send another message in which something else will happen. I have to go, right, this thing happens, and then it stops, and then the next thing happens. Now, why void returns? Design principle, important part of the programming language, making distributed objects more efficient. Turns out option C. The reason for having void return messages is so that you don't have to go back over the network to ask what the return value was at the end. And of course, we're all using distributed objects, which is why we all choose to use void return messages in our applications, right? Right? So, imagine that I wanted to do this instead. Here's a mutable object. I change it, and then I give back the object that reflects the changed system, which can also be done like this. And then my first object doesn't change. And the code that called into that object doesn't change either. But suddenly everything's gone from mutable to immutable, just by choosing which object you get back from a method. And when I was, so this company called Centec, about 2 years ago, 1993, created a thing called OC unit, which is like a port of Kent Beck's S unit to Objective-C. It's a framework for doing automatic testing of object-oriented code. And so I had my tests that went, like, let's just kind of mutate this grid, and then everything that happens, happens. And by making this change, I could go to none of my grids ever change, and so the one that I've got now and I'm trying to draw in my view is definitely the one that I'll always have forever, just by changing which object gets returned from this method. Building messages out of messages was my last rule. We already talked a bit about higher order messaging, but the other way you can do it is that a selector is basically like the name of a method to call, and you can go, hey, I need to call a method. So rather than going, I want to validate this menu item, which menu item did I get? If it was that one, I'll do that. If it was that one, I'll do that. If it was that one, I'll do that. And if it was that one, I'll do that. Why not just take the name of the menu item, take the name of the prefix for the method you're going to call, and create a new method, and then find out what the result is. So again, we've managed to move all of the conditions out of the system. There's obviously, there's a bool in there, so Next have an if statement in their framework, but we've managed to avoid one. So that's maybe what we should be doing in order to write object-oriented programs in Objective-C, which is not what we've been doing to date. What should we avoid? I like static type checking, I do. I like the fact that it's possible to get some of the maths of whether your program works or not evaluated before you actually give the program to anybody to try out. But an object-oriented type system shouldn't say, what did you call that thing that I've got right now? It shouldn't say, hey, what constructor did you use to build this object? It should say, what can this object do? And can it do the things you need an object to do? So it should be a structural type system, not a nominal type system. That means it should look at the shape of the parameter, not at the name of the parameter. And because Objective-C's type system, which is fairly new, it wasn't used very much in Next Step 3, but it is used in OpenStep now. Because that is a nominal type system, we're kind of forced to contort all of our object hierarchies and try to only use things that are subtypes of the thing that we were passed in. And that means we have to subclass everything, and subclassing is coupling, and we want to avoid coupling. So, unfortunately, there isn't really a language that has a structural type system. Self has one, but you can't use it because it's just used for optimizing message sends inside the runtime. Camel has one, but isn't object-oriented. I hear that, like right now, INRIA in France is working on an object version of Camel, an OCaml, and that might be out sometime soon. But right now, we can't use it. C, that's where all of the complexity comes from. It's where all of the null pointer exceptions come from because, nil is just a message thing. Like, sending a message to nil is fine. Using C on nil is bad. Returning void, we've already talked about. That leads to sequencing, and it leads to complexity. But above all, contorting your code to fit the arbitrary rules that I just told you is bad. It's all about the trade-offs. I don't know what you're laughing for. Ridicule is nothing to be scared of. So maybe you need to have heard the song. Anyway, these are rules, but these are design rules. This is, like, object-oriented programming is fundamentally about designing a software system. So if it turns out that your implementation would be faster, easier to understand, use less memory, any of these things, if you use C, I'm not stopping you, but it will be a lot easier to do if your design was object-oriented, because then every chunk of the application, every node that is connected by these interstices will be separate, will do a single very small thing. And so you can just swap it for something else, or you can take a group of them and swap that group for something else. So you might want to use object-oriented design. That doesn't necessarily mean you have to have an object-oriented implementation, but you can certainly start with one. Right, that's enough of 1995. Let's look into the future now. Let's see what, so the object-oriented crisis is upon us. It doesn't look like we're going to get out of it. I'm not worried about object-oriented programming. What I'm worried about is this thing, this talk that I've done. I want to fast forward 20 years, so like 2015, if you can imagine what computers will be like then, when your portable computer can run for like 3 years on 2 AA batteries. I want you to think forward to 2015 and think, so the object-oriented programming didn't help us because we didn't use object-oriented programming. We relied on the trapdoors to carry on writing C and claim we were doing object-oriented programming. I want to look at a language that's fairly current. It was created in 1989 at Glasgow University as a result of the Precambrian explosion of academic programming languages. So there's this there's this other way that's based on some maths that's kind of hard, and I'm not going to go into, of writing programs, and it says, always be functioning, never be sequencing, compose functions out of function. If I replace function with message, this is trying to do the same thing because it's trying to solve McElroy's 1968 components problem. It's trying to say, let's build little reusable blobs of software and then compose them into a system that is what we actually want. So My worry is that in 20 years we'll go through this again, and everyone will go, hey, functional programming, it's awesome. Or some other paradigm, maybe it'll be data flow programming or something like that, but they'll go, this is awesome, this solves all of our problems. And everyone will go, yes, it does. I don't understand how to apply it here, so I'll just use the trapdoor to write my C. So I know that that's kind of ending on a word of warning, and it's, it's not the happiest ending to a talk. But I thought that was important. I thought I better, from the perspective of us programmers in 1995, work out what problems we have to avoid as we go forwards, 2015 and beyond. So really, thanks very much for listening.